right, so we can get started. It is my pleasure to introduce Maani Ghaffari, who received his PhD in Australia, decided to come here to the cold. What a mistake. He's currently an assistant professor in the Naval Architectural and Marine Engineering Department, where he's been there since 2019, 2020.
17.
Well, I mean, as a professor,
2020.
Amazing. All right. He's won a bunch of awards, including an Amazon Robotics Award and whatnot. He's going to talk today about doing Lie group style stuff, control for robotic systems. He promises me there's an amazing video at the end.
I don't remember I promised that, but I do have some videos. So it's an honor to be here. I never imagined I'm going to give a control talk and giving you new results on geometric control in Michigan. Not being humble, because we were working on a lot of perception problems, and there are great progress in Michigan in geometric control. This is my lab. Recognize yourself in the crowd. So we work on a lot of field robotics, perception problems, planning, control when it's bothering us, and it makes us curious. We look into it. Today is about one of those problems. So what happened? This is the story and why I'm telling you some control results. So I've been looking into symmetry in robotics, and in particular in state estimation and perception problems. And generally, if you look into artificial intelligence and a lot of algorithms on state estimation, even old ones, probabilistic robotics, a nice part of the problem is the robot, the hardware, because that really connects the AI to the real world. And that's really exciting, because then we can eliminate all the problems that are not maybe relevant to the physical systems and focus on a much narrower part of AI that is coupled with robotics. That's the motivation. But robots are deeply geometric objects. They undergo 3D rotation and translation. So all the geometric notions that you learn in physics, dynamics, and kinematics exist for a robot. So people looked into a lot of mathematical frameworks for modeling robotics, but one of the most successful one is Lie group, matrix Lie groups. Lie groups are best tools we have in math for modeling continuous symmetry of a space. The action of a Lie group on a homogeneous space will move you from one point to another point without altering the space itself. So it's the symmetry of the space. It leaves the underlying space unchanged. So that's, for example, true for rotation, rigid body transformation, in computer similarity transformation, like the scaling and perspective change. So these are very powerful tools. And that's what we use. So the story starts where we looked into a state estimation problem. So the problem of a state estimation is that I have a robot, there's an inertial or world frame, the robot moves with all sort of movements, walking, running, jumping. We want to know how fast we're going, and we want to know where we are with respect to that reference frame in 3D. So we need a 3D orientation, we need a 3D position, and we need a 3D velocity. So the goal of robot state estimation is at the very least to estimate these quantities, but it could be more, like a map or bias of your sensors and so on. So back in around 2018, with Ross Hartley here and from Jesse's group, Professor Griez's group, we looked into this filter developed by Barou and Naval in France. They made a really beautiful filter by making the abstract symmetry preserving observers into something that is tangible. It was called it's called invariant extended column filter, because suddenly the abstract framework was very tangible. We could do algebra just like a column filter and run a Lie group, run a filter on Lie groups. So we decided to bring in contact and revisit the state estimation problem on regular robots. So we used IMU, contact data encoders. The magic was that you write down the filter, you derive the Jacobians, they're constant. In the deterministic case, for a complicated system like a robot, you derive Jacobians that are constant. This was very surprising, because before that, everything was nonlinear. You had to evaluate the Jacobians. That could lead to positive feedback loop, and observability analysis was very difficult. So now we could do observability analysis just like in linear systems in the Lie algebra. Tangent splits at the identity where the filter covariance is tracked. and the Jacobians are calculated. So that was the magic, and we got this result on campus. Arguably a major factor why I'm here. So then people could see that these things are not just for fancy, journal writings and showing off some equations. They actually work on the robot, and they really outperform all the old methods. So that was the proof that this is the direction. We need to dig in more and see what more we can do. So here we have the state estimator on the robot. This is around 2018. We are compensating the motion of a rotating LiDAR and bringing it into a common frame, and then accumulating that for, let's say, 10 seconds, and then I'm visualizing it. So that gives us a map. This is not a map, just a point cloud, but using just odometry. And you can see that in the camera view that this is very shaky, but the map is very stable. So as soon as we did this work, which we did some more work later, as soon as we did the state estimation, at that time with Ross Hartley, we talked, and we knew that there's got to be a dual for this, right? If there is a dual for LQE, and that's LQR, there's got to be a dual for LQE on Lie group. And that's going to be the equivalent of that. But we didn't get to solve it. Why? Because to look at the control, you need to talk about the dynamical system, and you need the equation of motion. Just kinematics is not enough. And we did not know what's the equation of motion in the Lie algebra. So 2 years, passed, and I've been working with Professor Block in the Department of Math. During a summer, I decided to read his book. He has a very heavy book on non-holonomic mechanics and control. So I decided to read his book instead of writing proposals. So ignore everything. I'm just going to learn dynamics and Lie groups. I was obsessed with this problem. Another background is that Tony sent me a paper, and it was so hard to understand. I was really bothered by that. So that motivated me more to just spend time and learn it. This is another state estimation algorithm. So it works really well on different robots. It's verified. By the way, I teach this now in Michigan. Michigan is one of the only places we teach in Vernikiev. There are extensive notes and lectures. So this was over, but we needed control to do all of that problem. So the trick was that learning that the equation of motion in the Lie algebra can be derived, and that's called Euler-Poincare equation of motion. These are equations of motion when you study the dynamics of a physical system in a body fixed frame. You study the problem in the body frame as the robot is moving, as opposed to the traditional inertial frame methods that we learn in Euler-Lagrange equation of motion. So that enables us to bring in the dynamics, and then the kinematics part was quite similar, so we could formulate the problem. So the work, the major drivers of the work is Sang Lee, my PhD student. He's the smarter than advisor student that you wish to hire. And William, which is my collaborator, and they've been instrumental in the results. So what is the problem? We want to track a rigid body, 3D rotation, and 3D translation. And we want to derive the same results. We want to have the system to be trajectory independent. That means we want to do some sort of nonlinear control, but not being affected by the current operating point. That's the expectation. So we're going to have tracking error defined by the group action. We linearize it in the Lie algebra. We show that this is a state independent. So the way it works is that for any Lie group, you have the kinematic equation of motion, which is defined by the reconstruction equation. This is the typical R dot equals R omega skew that a lot of you know, right? For any matrix Lie group, you have this matrix differential equation. However, the twist, the dynamics of the twist itself is governed by something that is called Euler-Poincare equation. This is the dynamics of the rigid body in the body frame, in the principal axis of the body frame. As you can see, the inertia matrix is constant. If you're observing everything in the principal axis of the body frame, there is no need to map the inertia matrix as you move. All those sine and cosine and troublesome terms in the mass matrix and Coriolis matrix, they're disappearing. Examples of this equation is the Euler equation. You're probably familiar with that. I omega dot equals omega cross I omega equals the external torque. That's the equation of motion often you see for quadrotors for the rotation part. This is a generalization of that. This considers the translation. You can even go to higher orders and consider velocity and other terms. So this was the key. Now we have the equation of motion in the Lie algebra. Notice that the equation of motion does not depend on the rigid body transformation itself. So you can integrate this without ever going back to the manifold, to the group. So this is very important. If we do want to, we can use the result, twist, to reconstruct the group element to get the path of the rigid body. So we have the flexibility of operating in the tangent space without ever going to the group. This is a major results we have in Lie group. Now define the group error define the error to be the inverse of the desired pose times the pose that you track. Take the derivative of that, you derive the aerodynamics of tracking. As you can see, the aerodynamics does not depend on configuration or your current configuration. Another point is that you don't get to just get the delta of two velocities for a rigid body as the robot is moving. If you look at the differential geometric aspect of the problem, these velocities are totally at different tangent spaces. So you do need a transport map, which in this framework is the adjoint map. So basically, you need to do a change of basis to map the desired velocity to where you are, or vice versa, to get the delta. This might, one of those things and say, who cares? We can just ignore it. But it turns out if you do that, then you get the results that you get exponential convergence, you get trajectory independence, and so on. All right, so we got the kinematic aerodynamics, right? And then we have the dynamics attached to it. New exotic equations. This is not usually we see in books. Let's linearize, because the error, the delta error, this is still on the group. I want to lift the problem to the tangent space in the Lie algebra, and I never want to come back to the group. Why? Because once you're in a vector space, we can use algebra, we can use the off-the-shelf QP solver. Everything will be beautiful for running and implementing a control on the robot. If you're working with a nonlinear problem on the manifold, it's very difficult to implement it and get good performance on the robot. So linearize this, and you do not see the current state, operating point in this equation. All you see is the desired twist, how fast you want to go and rotate, and the error itself. So given an initial condition for the error, but often you can read it from the observer, you can integrate the aerodynamics independent of how the robot is moving. This is the same result we had in the invariant filtering. On top of that, the equation of motion is still nonlinear. You could linearize it around some operating point to get the linear dynamics. But the key results is in the kinematic error, because we can accept this to be the linearized form because it doesn't involve the state anyway. All right, so when we do that, we can define the output to be your tracking error. So the tracking is the error of the orientation, 3D orientation and 3D position, plus twist. Form the output using matrix equation. Let's discretize it. This is not a fancy discretization. The true discretization should preserve the Lagrangian, preserve the energy. This is just the Euler discretization. Do that, and then you get the discrete time, basically LQR style problem, right? If you do it in a receding horizon manner, that will be MPC. You can add all your constraints, and you get the model predictive control in the Lie algebra. So you got the dynamics here, which is linearized, and it does not depend on your operating point. And U is the control effort. So what happens when you simulate a fully actuated rigid body. The previous result we had in the literature was the state of the art was this work from Berkeley. We had variational base, basically discrete time variational base linearization. They assume small rotation angle. So it works very well, but it prioritizes position. The first row is our method. The second row is variation based. It prioritizes the position. It depends on a small angle. When you initialize it badly in large rotation angles, it takes a long time for the rotation to converge. But what we can do, because we formulated in general for rigid body, we get simultaneous convergence, exponential convergence of rotation and position. There is another work from Ilya Kolmanovsky's group. That's a major result as well. So they prove actually exponential convergence for SO3 rotation group. But when you look at it for SO3, SE3, it's a simplified version of what we derive. Some of the off-diagonal terms are missing. So because of that, it ends up being a simplified version of what we do. So in that sense, it underperforms. But I have to say that that's a more general framework. Our method is more specialized, so we get better performance for this particular problem. Now, this is a big deal for robotics, right? Before that, we couldn't do this. Nobody could, formulate exponential convergence of 3D rotation and position. We implemented this on legged robot as well. You need to add friction constraints and some other basically external forces. So the goal on a legged robot is that to run a model predictive control so that you can estimate ground reaction forces and torque on the robot. Once at every step, you know the ground reaction forces on the robot, and the body of the robot, you can distribute that force and torque using the transpose of the Jacobian to every joint. From there are multiple methods like whole body control, and maybe you can just use a PD control to track it. So in robotics, we don't stop when we just simulate. So we have to run it on the robot. If it doesn't work on the robot, then it's not good enough. So Sangli implemented this on the robot with Dianha. Dianha is a master student. He graduated. So for some basic tasks, like you want to rotate, it does. It's a little hard to see in the small plot. It does give you better convergence and less steady state error. We need more exciting videos, Sandy. I am bored. This is so long. The paper got accepted. I think the theory is ahead of the experiment a little. So another motivation is that recently I learned from Toyota Research Institute. They, for example, they have race cars, right? They suddenly get interested in this method because if you're using autonomous racing and drifting, for example, right? Sounds like a good idea if your model predictive control on the car does not depend on your operating point. If you're running in a linear MPC, which is the case right now, instead of a convex MPC that I presented, you're going to be affected by extremes of the car behavior. And that sounds to be troublesome because you're operating at the limit of handling for tire and road friction. So this is very attractive for that domain as well. Okay, we did that. And the question is, can we prove the stability? That means that now that we can move everything to a vector space, can we also prove the extension of linear system results to these linear exponential models, Lie group models?
Yes, yes, sir.
We're going to pretend nothing happened. So how can we verify stability? This is again work done by Sangli and collaborator Will. and other more senior people who don't need my promotion. So now we want to do control and Lie group, but we want to relax it a little bit from that robotics problem. We want to go back to the LQR style problem. Imagine we can do infinite horizon. We can just relax the constraint. What is the reason why we can't get a certificate of optimality? So it turns out the whole insight is in how you design the cost function, right? Now, this part is Sangli's contribution. I told him that we should lift the problem to the Lie algebra and never look back. For some reason, I know we should do it because of the state estimation, right? Then he looked into the literature and he realized that the problem is the cost function, because everyone is defining the cost function on the manifold. For example, using a trace function or chordal distance, which is basically a straight line distance on a nonlinear manifold. And when they do that, the cost function is radially bounded. You don't want a radially bounded cost function in control, because then if you want to use Lyapunov theory for stability, you want a derivative to be unbounded, so you can basically have a vanishing error to 0. So this is clearly not good. You don't want that. And it happens for the rotation part, and it's really troublesome, as we'll see. So we're going to do a Lie algebraic version of it. So the rule of thumb is that in the probabilistic method, they say Bayesian version of everything is better. If you do everything on Lie group, it's better. If you do a Lie algebraic version of that, it's also better. So you just follow this insight, and like me, you'll get a job and you can buy a house with a mortgage and whatnot. All right, so let's lift the problem to the Lie algebra and imagine we could show that there is a quadratic function that basically gives us the stability. So if we have a quadratic function in the Lie algebra, which is basically the log of matrix logarithm of the error, we're always working with the error, right? Everything is error state. We never work with the actual trajectory. This is the correct way of parameterizing the problem. So we take the log of it, and then you get a quadratic function. This is radially unbounded, so that's good. But the problem is the derivative of the matrix logarithm is not that easy. It's a pretty nasty series, and you're going to panic. When you look at it, you have to take a derivative. You don't know how to get rid of the infinite series that you deal with. So the question is how to get a gradient of the log map. Now, this is the reason I was holding back the literature from proving this, because if you don't exploit the symmetry, some terms won't just vanish. It's not that trivial that you just get simplified results. The insight here is that on matrix Lie groups, all tangent spaces are isomorphic. If you know the Lie algebra of the matrix group, you know everything about the manifold. Up to, let's say, a left translation, they're the same. So they're isomorphic. So we can always stay in the Lie algebra and never operate at other points. And that's the symmetry of that space. So for every Lie group, you can define a left-invariant metric. Suppose Lie algebra is a vector space. So suppose we define a metric, a quadratic metric, an inner product, using a positive definite matrix P. It's left invariant because at any other tangent space, you could transform this to the metric in the Lie algebra via a left translation. And left translation, the push forward map, it will be just a matrix group that's multiplying from the left. So it will cancel this push forward map, will cancel the translations. It's x inverse times x. You get the inner product back in the Lie algebra. So if you define a metric in the Lie algebra, you are inducing a metric on every other tangent space. And you can just easily go back and forth. This is not new, right? So you open every lecture note on Lie groups. At some page, they're giving you this, right? So it's nothing surprising. To get the gradient, suppose my function is of this form. Now, by definition, the differential of the function, right, is defined by the inner product. The gradient, by definition, is the inner product of basically any vector, right? By the gradient, that will give you the differential of your function. So pick some basis. We do not need to know what that basis is, which makes the proof coordinates free and beautiful. Do a left translation because we want to be at where we are, where the error is. We cannot stay at the identity and work with a gradient at that point. Do a left translation. Now we are at the new metric. At this point, because this is the definition of the basically differential of the function, then we learn that this is the gradient, the left-hand side. And the right-hand side is just the equivalent of that vector in another tangent space, which you could see this from the reconstruction equation as well. So the proof is ridiculously simple, right? So you just shift some terms in the metric. You don't need to open anything, and it's coordinates free. No matter what basis you choose, this is true. So the gradient of the log map is this. It's no mess, no extra term. I know some of you are questioning the result, but established mathematicians stamped it. All right. Now, from there, we can get the theorem that suppose the kinematic systems from the reconstruction equation, that's the equation of motion for a rigid body, for example. And suppose I'm given a gain matrix that is Horowitz, all the eigenvalues are negative. The matrix is negative definite. Form a linear feedback based on the error in the Lie algebra. So it's basically k times log of x. This linear feedback can exponentially stabilize the system to the identity. This is equivalent of the linear system results for matrix Lie groups. To prove this, you can start from the time derivative of your cost function, which by definition, again, is the gradient, its inner product with x dot, which is the vector at tangent space x. Now substitute the feedback to look at the closed form system, you get this inner product. Using the symmetry, let's go back to the Lie algebra, x will disappear. And you can write down this using a quadratic function, right? Which we define it as q. And then you get the Lyapunov equation. This is very much like the linear systems. So, given any q that is positive definite, we know that there is a p for that cost function that is positive definite. This is the existence of the quadratic cost function for the control problem. You can prove it like this. Then from there, you can just open a textbook. I'm sure that's what Sangli did. You open a textbook and then you show that the derivative of, if the cost function is quadratic, if its time derivative is also quadratic, then you can show that the time derivative of your cost function is bounded above, right, by the negative of some constant times your cost function, which means the error will exponentially decay to zero. This is the Lyapunov stability theorem. Pretty beautiful. Let's go back to the tracking problem. We want to track the same system, the kinematic equations, the same aerodynamics, same equation of motion in the body frame. The baseline that I'm going to show is what you see in the literature. They typically use this sort of feedback and some feed-forward term, which is based on the dynamics to get something that resembles like computer torque control. You have a feed-forward term, right? Don't ask me why, but that's what they do. Now this term, if you, for example, for SO3, which is this example, this term is equivalent of sine of norm of your angle divided by the norm of the angle times your angle as a vector or its direction. Now this is already troublesome. If you are operating at the norm of the angle around pi, right? 180 degrees. What happens? This will vanish. The gradient will vanish. You are at the maximum error and the controller is making no effort to moving you. So that's doesn't seem like a good controller for aircraft. Wants to escape an enemy missile, right? You're going to be frustrated if you're sitting there. We propose to build a linear feedback, just like a linear system. A gain PD controller, a gain times the error in the Lie algebra, and a gain times its derivative. This is the derivative of, what is it? This is the derivative of, this is the angular velocity, basically. E dot is the angular velocity. So it makes it PD, angle and angular velocity. Now we simulate this with really bad initialization near pi. When the angle initially is at pi, our controller exponentially will decrease the error because it's guaranteed. This is the canonical problem for what we proved. The other controller, it takes a long time because basically the feedback, the gradient will vanish at pi. So the trajectory is simulated using some sine waves here. So we get significant boost here for this controller. Now we can do LQR style trajectory optimization. This is not just good for the controller, we can do also trajectory optimization. To plan a rigid body trajectory for a robot or a quadrupedal or any object that moves in 3D, we want to design LQR or MPC style trajectories. Okay. It's going to be iterative LQR, just like the invariant EKF was invariant extended Kalman filter. Because this problem at the end of the day is nonlinear. The space is not linear, so we have to iterate. So what we do, we run our method, which will give us iterative LQR and Lie group. This is basically a linear trajectory planner. So we expect a linear convergence here. Do we have time? Yeah. And the other baseline is differential dynamic program. Now, differential dynamic programming is a very powerful method, and it's a second order method. So you expect to get quadratic convergence. So what we do, we from a very important work that is very recent as well, we get this DDP method, we run it as is, but we also change its cost function to the cost function we designed the Lie algebra. See what's the difference. And we do a forward backward. From the forward pass, we roll out the system trajectory. In the backward pass, we compute the optimal policy, which is here the feedback gain and basic feedback gain. To rotate the rigid body from some rest condition to how much? 179 degrees. Now, as expected, all three methods, of course, can solve this problem, right? But what you get from this, our new result is, as expected, linear convergence. It will converge, it's guaranteed. The DDP that we took from the literature, TAC paper 2021, it converges very slowly in terms of number of iterations. We change the cost function, we get this blue curve. This is what you expect, right? If you run gradient descent and you run Newton's method for a problem that is truly quadratic, you expect quadratic convergence. So that's what we're seeing here in the blue curve. So the difference is huge. So there's no way the LQR method can, get the same, because LQR is supposed to have linear convergence, right? But differential dynamic program is a second order method. So to summarize, by just looking at the symmetry of the problem and how things evolve in the body frame attached to the robot, we could substantially reformulate what we did basically previously in a sort of ad hoc way, because what we used to do, we separate rotation from translation or do part of it correctly for the rotation and then ignore the translation. We're doing it simultaneously for all the degrees of freedom that we have on the robot. So our result was a linearization that does not depend on your operating point. That's very important. That enables safety, convergence, stability, many good properties for a robot. We can give a stability certificate using just property of the Lie groups. It's coordinates free. And this is basically the extension of linear systems to linear exponential systems. Matrix Lie groups are linear exponential systems. We can also accelerate trajectory optimization. And the message is you get these results if you study the problem in the Lie algebra. What can we do in the future? So many things, right? You just don't have time. If you're watching this talk, feel free to reach out or just do it by yourself. And send us your work, we will read it. Consider multi-body system, right? We're talking about single rigid body. Obviously, a robot or any complicated system has more mass distribution than lumping everything into a single rigid body. But we have pretty good ideas. We can do that. We can actually extend these results to multi-mass systems and replicate same problems. You just have to define your constraints carefully. We can revisit a lot of problems in the Lie algebra. A celebrated method is called control barrier functions. Now somebody can come and look into control barrier function in the Lie algebra. If you just define that, that's like a low-hanging fruit to get major results. For Sangli, that's a low-hanging fruit. So Sangli should hurry up now, putting all the ideas out to accelerate science. So we can also certify the region of attraction. The problem with constraint problems is that those LQR stability results are not necessarily true when you have constraints. You do need to study the region of attraction for your controller. So looking into basin of attraction of the controller for different problems is interesting. And basically many more, because from here, the sky is the limit, right? You can look into LQG. The separation principle is proved already for Lie groups. That's like 10 years old results. You can have the same separation result. You can look into LQG, for example. We're not doing it, so. What's coming up next? Is this the end for us? Absolutely not. It turns out, so Sangli took Tony's course, Professor Bloch's course on non-holonomic mechanics and control. Then he learned about Lie group variational integrators. So these are symmetry preserving integrators that preserve the energy of the system. And they operate a Lie group. What he discovered is that now, as soon as he learned that, he knew some polynomial optimization. As soon as he learned that, you can see that you can write your equation of motion as polynomials. They are directly polynomials. So you can just write down a polynomial optimization for a dynamic, dynamic, basically, trajectory optimization and control. So that's very interesting and exciting because, as you know, we can now solve for globally optimal solutions. Obviously, my advice is that we should do it in the Lie algebra. So one problem is that the Lie algebra integrator that we use is Euler. It's not energy preserving. So it's lagging behind these variational integrators. But I think in practice, it gives good results. Theoretically, it's a deeper problem. So in polynomial optimization, some preview of the results that is our next work. In polynomial optimization, you can lift the problem. The expert is here, Ram. You can lift the problem to infinite dimensional space, and do all of that space is a moment of space, and you can work with basically all the moments of your polynomials, and it will be giant optimization. It will blow up all the variables, but there's a theorem from basically this method that says that the solution that's rank 1, that's the globally optimal solution. So there are solvers for it. When you implement your problem and solve it, if you can, because sometimes it's too slow, you can check the solution. The solver will tell you when it's rank 1, you know that's the globally optimal solution, because you can look at the dual and then the gap is 0. Okay. So what happens? That's a 3D drone landing. There's a drone. I told Sangli we need photorealistic simulator. I'm tired of showing drone to be this a coordinate frame. But for now, use imagination. This is a 3D drone, and again, SE3 rigid body. We want to plan a landing trajectory, and we want to find the best solution. Now we can do it with constraints too. This is the results of unconstrained problem. So we can lift the problem and solve it using polynomial, and what happens, you check the solver and the solution is rank 1. That means that we don't have a theorem to prove that this is globally optimal, because the proof needs a careful, knowledge of the problem, because if you're not careful, you might claim something that's not true. But empirically, it's giving the globally optimal solution. Collaboration with a friend in JPL, so sounds like a good tool for NASA. So we're going that way, and hopefully I will steer something back to Lie algebra. Next year we'll have some results on that. So I want to thank our collaborators, Sangli, Dianha. It's not with us anymore. It's back to China, graduated. William, very talented mathematician. When I collaborate with him, I feel I have superpower. So I can go and make a mess, and I'll come and clean everything. It feels great. And of course, Professor Black and Professor Vestuvan, they were also our collaborators in this talk. With that, I take any questions. I will thank the sponsors too. All of you should be expert on Lie group methods for control.
So this isn't my area at all. So
Oh God.
ask a million questions. There's an aspect of this that I'm not getting, and so you're talking about controlling lowercase psi as the which you said was the so capital Psi is the exponential of lowercase psi.
That's true, right?
And you're controlling capital Psi to be to equilibrate it around the identity matrix, right?
Right. As a regulator problem, we want to drive the error to 0 or identity.
Sure. So now my question is, don't you lose something when you go to control? You're doing a linear control over a lowercase psi. Don't you kind of lose an aspect of rotational symmetry where you go around 360 degrees, you're back where you started in the original frame, but that's not the case for your linear controller. So do you see what I'm saying? Like
You mean the angle, because the angle is constrained between minus pi and pi?
Right. So isn't there a problem if you want to get to an angle of 0 and you start rotated all the way around, is there a distinction in your system between that rotated system and the original system, even though they're in the same configuration?
I think I understand the question. So the question is, the angle can produce discontinuity in the control law. Is that true? Is this problem that the angle is a circular quantity, and then we go from pi to 360 or minus pi to pi, right? And then there's a jump from negative value to positive value. So this actually,
But you're converting it to a linear system without constraints.
Mhm.
So that's what I don't get.
well, the Lie algebra of SO3, it does have that constraint. We don't go around again and again. So the angle is, you know, maybe between minus pi and pi.
It's just sort of implicit in your
Implicitly,
formulation.
that's the case.
Okay.
That's right. But a better answer for that is that in Professor Kolmanovsky's work, they proved that the control law is discontinuous, right? And the log map will give discontinuous control law. So the control, the feedback can become discontinuous because of this problem. But that's not a problem for the convergence. In fact, the theorem says in their paper that if there's any control law that will exponentially stabilize the system, will be discontinuous. There's no way we can get the continuous control law. And that's because of the topological constraint of the SO3, because if you have axis angle, the pi rotation about an axis, right? It's the same thing as the pi rotation about the negative of that axis. And that topological constraint will not go away in the axis angle representation. So I think the consequence of that is discontinuous feedback. But doesn't seem to be a problem on the robot, but we haven't maybe, you know, ran extensive experiment to see if this is really a problem.
Think about it. I'm just still not sure where that discontinuity shows up in your when you impose your feedback in your in the lowercase psi coordinates, which appear to not be constrained. You're saying that all that you require in capital K is that it be Hurwitz.
So you would expect, for example,
So you know, right there.
was it here, for example, this is SO3, right?
Yeah. So don't you also have to have some added conditions on that controller that keep lowercase psi from sort of. I'll think about my question and maybe.
I think the question is really good. You're asking when that discontinuity shows up, right? I'm not
It's
giving the
it should
answer
show
to
up
that.
somewhere.
Right,
You can't just get rid of
No,
it.
no, that's a really good answer. I don't have. I wish I had the control input plots. I don't know if this example will give us an answer, but so the question is when that discontinuity shows up. I don't have an answer to say, if you run this experiment, you will see it. But maybe if we run enough simulation and then plot the inputs, we could nail down
All right.
some initial guess. Shangli, do you have a better answer?
Yeah. I think the answer is that if we, for example, initialize the angles to 180 degrees, that's a singular point. Yeah. So that will not rotate. But the log map gives you maybe 180 or minus 180, depends on how you identify that point. So that will give you a different directions. If you add a little perturbations, it will, for example, 179 degrees, it will go one way. If you have 181 degrees, it will go the other ways. It depends on how your log map is working.
But don't you have a situation where your trajectory can go, your log map trajectory can transition from 179 to 181?
Yeah, I think that's a problem of this work.
That's what I'm trying to get at. Is it? I mean, don't you have a wrapping issue with your angle and it going past wherever the constraint is?
We can go along the longer geodesic instead of the shortest one, right? Right. So maybe I just say it for the Zoom. I don't know if it's recorded. So that if there is a little perturbation, right, we're operating at minus 179, and that could shift it to maybe some positive angles, right? The other side of the interval, then the controller will rotate, let's say, from the other side of the sphere, and then we go along a longer path. That could be a problem, especially if we introduce noise, I think, to the system. So I don't see how we fix any of that problem. But just the fact that we can drive the error to the identity no matter what direction. I think with some engineering that's fixable. I don't know if theoretically we can do something about it. You guys are the expert in aerospace. So any easy questions? That question was a nightmare, right?
Can you say anything about the sparsity of the cost evaluation? So if you take your, if you transform your cost and make it more linear and convex, does that take away, does that just make all the computation more sparse? And does that have any noticeable effects on like latency or power or whatever, the computation?
It does. It's the whole point of. So the question is, what's the implication of this convex MPC on latency and runtime? If it's not a convex MPC, at the very least, it's not a QP and it's a sequential QP, right? That means I have to compute it many times, several times. So that's usually undesirable. The convexity, that means that I only plan once for a receding horizon controller. That's the best you will get, no matter how many times you run it, right? But it is faster. This is one motivation I didn't mention. Thanks for pointing it out. So the convexity implies faster runtime on the robot. Otherwise, nonlinear MPC or sequential quadratic programming will have to run it multiple times for one step.
There would probably still exist application spaces where, well, are there still applications like you would have to have MPC running the cost many times if you could turn every single problem to a convex thing, right?
If you turn every single problem into convex, you don't have to run it many times. But the question is, how are you turn it into a convex problem? Is it just a naive linearization and evaluating your Jacobian? Or is the linearization that I presented that it is trajectory independent? You do not need to evaluate it as you change your operating point. So that's the same result in the invariant extended Kalman filter, right? So the convexity doesn't come at the cost of losing accuracy of the model. It's just the intrinsic property of the model that the linearization is constant. The linearization gives you convex problem.
Is it fair to say that every problem just has like different levels of how difficult, let's see, how difficult it is to make it convex, or is it like there are just some that are just impossible to convexify? Well, is that convex?
That's a good question for Ram. The question is, can we say how difficult is this problem to make each problem convex? First, I want to point out that this was about control on matrix Lie groups, right? It is not about any systems. The system must be evolving on Lie groups. The broader answer to that, which I'm stretching myself a little to answer, is that every problem is convex. You can lift it to some infinite dimensional space to solve it, but the problem is it becomes intractable. Out of those intractable problems, those that possess some sparsity pattern, then they become sort of tractable, right? So that's the broad answer, but I don't think it's directly related to what I presented. So this is specific to Lie groups. We have no claim on general smooth manifolds. Yeah. These questions are hard.
One more. But
Ask about robot. How did you run the robot?
I want to ask a question about the iterative LQR.
Mm-hmm.
Yeah, it says it has slower convergence compared with PPD, right?
DDP, right?
So why we prefer ILQR in this case? Is it because of computation?
So the question is, ILQR that I presented shows linear convergence or superlinear, whatever, close to linear, right? DDP with the new cost function can give quadratic convergence. So why on earth somebody should use our ILQR, right? Well, why don't you, use second order optimization to train a neural network? I mean, you would if you could, right? So this DDP is using all the second order derivatives. Now you could say that I can sit down and calculate all of them. In this case, possibly you can derive the closed form once. It could be complicated, right? If you can, yes. But if you have to do all of them using automatic differentiation, it will make it slower. So let me distinguish. It's faster in terms of number of iterations. So mathematically, it's faster. Less number of iterations. Time-wise, if you time it, I'm not showing here. You could go either way based on how you implement it. I believe DDP methods are using automatic differentiation in this implementation, as I remember.
Well, thanks, Maani. Congratulations. This is the most well-attended seminar we've had in a few minutes. I was going to say we ought to have a robotics seminar next week, and then I realized we are having a robotics seminar next week. So see if you can outdo him. Okay, so give him a lot of applause.
Thanks everyone for showing up. Next week is exciting. Heroes talk.
You know, when I started off in this field back in the 80s, it's one of the whole big research areas with geometric linear control and
Yeah.
with lead groups. I mean, Jesse Grizzle wrote his PhD dissertation on systems.
I know.
And so this is really kind of a blast from the past. I thought about it for years.
It's they never go away.
Anyway,
Thank you.
I gotta run. But I'll
Thank you.
see you.
Thank you.